Let's begin our exploration of the wave function and Schrödinger's equation by considering a concrete example. The system I propose to look at is the simple harmonic oscillator, an important paradigm in physics. The system comprises a particle of mass m connected to a solid wall by a spring with spring constant k. There is no gravity present. The only force acting on the particle is the restoring force from the spring. The particle's motion is strictly one-dimensional, confined to the x-axis. We'll set the origin of the x-axis to correspond to the particle's equilibrium position, where there is no force acting on it. With this choice of the origin, the particle's potential energy is half the product of k and x squared. The force, as the negative gradient of the potential, equals minus k times x. Now, to simplify the forthcoming calculations, let's introduce the quantity omega as the square root of the spring constant divided by the particle's mass. Omega, possessing dimensions of frequency, will indeed turn out to represent the frequency of the particle's oscillations. In terms of omega, k becomes m times omega squared. The potential V becomes half the product of m, omega squared and x squared. And the force reads minus m omega squared x. Let's begin by analyzing the system using classical mechanics. Here is the Newton equation: mass multiplied by acceleration equals the force acting on the particle. As you can see, the mass can be cancelled on both sides and drops out of the equation. We also need to specify the particle's initial position and velocity. Let's call the initial position x sub 0. As for the initial velocity, let's set it to 0 for simplicity. Physically, our initial conditions imply that the particle starts at rest from the point x sub 0. The Newton equation and the initial conditions completely determine the particle's trajectory. As one can easily verify, the trajectory is described by the following relationship between x and t. In line with intuition, the particle executes simple sinusoidal oscillations along the x-axis, characterized by frequency omega and amplitude x sub 0. Now, let's look at the same physical system from a quantum mechanical perspective. The particle is now described by a wave function psi, which follows the Schrödinger equation. It's the same Schrödinger equation as before. The only change I made was putting the explicit form of the potential V into the second term on the right-hand side. Just as in the classical mechanics case, we need to specify the state of the system at time t equals 0. Let's say that initially, the wave function takes the shape of a Gaussian packet centered around the point x sub 0, the same point where we positioned our particle in the classical mechanics scenario. There are two additional constants that parameterize the Gaussian packet, c and alpha. C represents the amplitude of the packet, which we won't discuss further for now. As for alpha, I'll set it to a specific value given by m times omega divided by twice h bar. This choice of alpha is purely technical, as it significantly simplifies all calculations and results. Finally, to ensure our mathematical problem is well posed, we must impose boundary conditions. In other words, we need to stipulate the value of psi at the boundary of our domain, which, in our case, extends infinitely far away from the origin. Actually, on the left, our domain is bounded by the wall, but let's assume that the equilibrium length of the spring extends to infinity. For reasons that will become apparent later, the only physically meaningful boundary conditions are those that require the wave function to vanish as x tends to plus or minus infinity. The mathematical problem defining the spatio-temporal form of the wave function psi is now well posed. Here is the solution to this problem. For clarity, the x-dependence of psi is denoted in red, while the t-dependence is highlighted in purple. Verifying that the presented function indeed satisfies the Schrödinger equation, along with the initial and boundary conditions, is deferred as an exercise. I encourage you to tackle this exercise diligently, as it provides valuable practice and prepares you for similar calculations in this course. Rest assured, the complete solution is provided for you to verify your own calculations against. Our next step is to attempt to make some sense of the obtained quantum mechanical solution to the harmonic oscillator problem.